In the vast darkness of space, something extraordinary travels at unimaginable speed. Light itself moves through the cosmic void, carrying with it the stories of distant stars, the whispers of galaxies billions of years old, and the very essence of time and space as we understand them. Picture a single beam of light beginning its journey from a star so far away that when it finally reaches your eyes, civilizations may have risen and fallen on distant worlds. This light has traveled for eons, moving at exactly 299,792,458 meters per second. Never faster, never slower, always constant. But what if this fundamental truth, this cosmic speed limit that governs everything we know about reality, is not what it appears to be? What if the speed of light, this seemingly absolute boundary of our universe, is actually an illusion born from our limited understanding of existence itself? For centuries, brilliant minds have measured, calculated, and confirmed this cosmic constant. Scientists have built their greatest theories around it. Einstein himself declared that nothing can travel faster than light, weaving this principle into the very fabric of space-time. Yet as we peer deeper into the mysteries of quantum mechanics and explore the strange behaviors of particles at the smallest scales, cracks begin to appear in our certainty. Consider this remarkable fact. From the perspective of light itself, time does not exist. A photon that begins its journey from the surface of the sun experiences no passage of time as it races toward Earth. In its reference frame, the 8-minute journey that we observe happens instantaneously. The photon exists simultaneously at its point of departure and arrival. How can something that experiences no time have a finite speed? This paradox hints at something profound. Perhaps the speed of light is not truly about speed at all, but about the nature of reality itself. Maybe it represents the rate at which cause and effect can propagate through the universe. The cosmic speed limit, not of motion, but of information and existence. As you drift into contemplation, imagine floating in the emptiness between stars, watching as waves of light wash over you from every direction. Each photon carries information from its origin, painting the story of the universe in electromagnetic radiation. But what if these messengers of light are not bound by the limits we perceive? What if there are deeper layers to reality, where the familiar rules simply do not apply? Tonight, as you rest, let your mind wander through these cosmic mysteries. The speed of light may seem like cold, hard science, but within its mystery lies poetry. It connects the smallest quantum interactions to the largest galactic structures. It links the immediate present to the ancient past. It bridges the gap between what we can measure and what we can only dream of understanding. The question we explore together is not merely scientific, but deeply philosophical. If the speed of light is an illusion, then what does that say about the nature of time, space, and reality itself? Are we prisoners of our own perception, forever limited by the biological and technological constraints that shape our understanding of the cosmos? Or perhaps the true illusion is thinking that there must be limits at all. In the quantum realm, particles seem to communicate instantaneously across vast distances, defying our classical understanding of space and time. In the cosmic arena, the expansion of space itself may carry distant galaxies away from us faster than light can travel between them. These are not merely abstract concepts for physicists to debate in ivory towers. They touch the very core of human experience. Every time you see a star in the night sky, you are looking backward through time, seeing that star not as it is, but as it was when its light began its journey to your eyes. The speed of light is not just a cosmic speed limit. It is the rate at which the past becomes the present, the velocity of causality itself. The story of measuring light's speed begins with human curiosity, reaching across impossible distances. Long before we had the tools to measure something moving so incredibly fast, ancient minds wondered whether light traveled instantaneously or took time to cross the heavens. Imagine standing on a mountaintop at night, holding a lantern and trying to signal to a friend on a distant peak. You flash your light, and your friend flashes back. Could you measure how long light takes to travel between you? For centuries, this seemed impossible, because light appeared to move without any delay whatsoever. The first person to seriously tackle this puzzle was a Danish astronomer named Ole Rømer in 1676. He was not trying to measure light's speed at all. Instead, he was carefully timing the eclipses of Io, one of Jupiter's moons. As Earth moved closer to and farther from Jupiter throughout the year, Rømer noticed something strange. The eclipses seemed to happen earlier when Earth was closer to Jupiter and later when Earth was farther away. Rømer realized he was witnessing something profound. Light from Io's eclipses was taking different amounts of time to reach Earth depending on the distance it had to travel. He calculated that light took about 22 minutes to cross Earth's entire orbit around the Sun. While this measurement was not perfectly accurate, it proved for the first time that light had a finite speed. This discovery changed everything. Light was not instantaneous. It was fast, incredibly fast, but it still took time to travel from place to place. The universe suddenly became a place where distance and time were intimately connected through the speed of light. As centuries passed, scientists developed more precise ways to measure this cosmic constant. In 1849, French physicist Hippolyte Fizeau created an ingenious experiment using a spinning gear wheel. He shined light through the gaps between the gear teeth, bounced it off a mirror 8,000 meters away, and measured how fast the wheel had to spin for the returning light to pass through the next gap. His measurement came remarkably close to the true value. Then came Albert Michelson, whose obsession with precision led to increasingly accurate measurements throughout the late 1800s and early 1900s. Using rotating mirrors and careful geometric calculations, he refined the measurement to extraordinary precision. His work established that light travels at approximately 299,792,458 meters per second in a vacuum. But what does this number really mean? To grasp the incredible speed of light, consider that in just 1 second, light travels a distance equal to circling Earth's equator more than 7 times. In the time it takes you to blink your eye, light could travel from New York to Los Angeles and back again 25 times. When you flip a light switch, the illumination appears instant to your perception, but the light from that bulb is actually racing outward in all directions at this fantastic speed. Every photon leaving the bulb spreads through your room, bounces off walls and objects, and enters your eyes, all within tiny fractions of a second. This speed becomes even more meaningful when we consider astronomical distances. The light from our sun takes about 8 minutes and 20 seconds to reach Earth. This means that when you see the sun in the sky, you are seeing it as it existed 8 minutes ago. If the sun were to suddenly vanish, we would continue to see it shining for 8 more minutes before darkness arrived. The nearest star beyond our sun, Proxima Centauri, is so far away that its light takes 4 years and 3 months to reach us. When astronomers look at this star through telescopes, they see it as it existed 4 years ago. They are literally looking backward through time, using light as a messenger from the past. Consider the profound implications of this cosmic speed limit. Light from the Andromeda Galaxy, our nearest major galactic neighbor, takes 2.5 million years to reach Earth. When we photograph Andromeda, we capture light that began its journey when early human ancestors were first learning to use stone tools. The photons entering our telescopes today carry information about a galaxy as it existed in Earth's ancient past. This relationship between light's speed and time creates what physicists call the observable universe. We can only see as far as light has had time to travel since the beginning of the universe. Beyond this cosmic horizon lies a realm forever hidden from our direct observation, not because of technological limitations, but because light from these distant regions has not yet had time to reach us. The speed of light also determines how we experience causality itself. Events cannot influence each other faster than light can travel between them. This creates a fundamental structure to reality where cause and effect are limited by light's cosmic speed limit. Press a button here, and its effect cannot appear instantly somewhere far away. Information, influence, and causality all must respect this universal boundary. Yet, even as we have measured light's speed with incredible precision, using atomic clocks and laser interferometry to determine its value to numerous decimal places, questions remain. Is this speed truly constant under all conditions? Does it change over cosmic timescales? And most intriguingly, does this speed represent a fundamental limit of reality, or merely a limit of our current understanding? Modern physics has built entire theoretical frameworks around the constancy of light's speed. Einstein's theories of relativity use this speed as a cornerstone, showing how time and space themselves bend and stretch to ensure light always travels at the same speed, regardless of the motion of its source or observer. This led to the revolutionary insight that time is not absolute but relative, flowing differently for observers, moving at different speeds. As you contemplate these mysteries, imagine light as the universe's messenger, carrying information across vast distances at the maximum possible speed allowed by the fundamental structure of reality. Each photon that reaches your eyes has maintained this precise speed throughout its entire journey, whether it traveled from a nearby lamp or from a star billions of light years away. The measurement of light's speed represents one of humanity's greatest intellectual achievements. Yet it also opens doorways to even deeper mysteries about the nature of existence itself. In 1905, a young patent clerk in Switzerland named Albert Einstein was pondering a strange puzzle that had been troubling physicists for decades. Light seemed to behave in ways that defied common sense. No matter how fast you moved toward a beam of light or away from it, the light always appeared to travel at exactly the same speed. This was unlike anything else in human experience. Imagine running towards someone throwing a baseball. The ball appears to approach you faster than if you were standing still. Similarly, if you run away from the thrower, the ball seems to approach more slowly. This is how we expect everything to behave, but light refuses to follow these rules. Whether you race toward a flashlight beam at tremendous speed or flee from it just as fast, the light always reaches you at exactly 299,792,458 meters per second. Einstein realized that this strange behavior of light was not a quirk or measurement error. It was revealing something profound about the very nature of space and time. To understand why light always travels at the same speed, he had to completely reimagine reality itself. The breakthrough came when Einstein proposed that space and time are not separate, independent things, but are woven together into a single fabric called space-time. This fabric can stretch, compress, and bend. When you move very fast through space, time itself slows down for you compared to someone standing still. When you experience strong gravity, both space and time warp around you. This radical idea means that the speed of light is not just a speed limit for objects moving through space. It is the speed at which space-time itself propagates cause and effect. It is the rate at which reality unfolds, the cosmic speed limit not just for matter and energy, but for existence itself. Consider what happens when you try to approach the speed of light. As you accelerate faster and faster, something remarkable occurs. Time begins to slow down for you relative to the rest of the universe. If you could somehow travel at 99% the speed of light, time would pass about 7 times slower for you than for people back on Earth. A journey that takes you 1 year would appear to take 7 years to observers watching from Earth. This is not science fiction or theoretical speculation. It is measurable reality. Particles in accelerators regularly approach the speed of light, and we observe their internal clocks slowing down exactly as Einstein predicted. Muons created in Earth's upper atmosphere by cosmic rays should decay long before reaching the ground, but they live longer than expected because time passes more slowly for them as they race through the atmosphere at nearly light speed. But time dilation is only part of the story. As you approach light speed, space itself begins to contract in the direction of your motion. From your perspective, the universe ahead of you appears to flatten and compress. Distances that seemed vast when you were at rest now appear much shorter. The faster you go, the more space contracts, until at light speed, distances in your direction of travel would shrink to zero. This creates a fundamental barrier. To accelerate any object with mass to the speed of light would require infinite energy, because as you approach light speed, the object's mass effectively increases without limit. The universe itself prevents anything with mass from reaching this ultimate speed. Only massless particles, like photons, can travel at the speed of light, and they must always travel at this speed. They cannot slow down or speed up. Einstein's famous equation, energy equals mass times the speed of light squared, reveals the deep connection between matter and energy through light's speed. This equation tells us that mass and energy are different forms of the same thing, and the speed of light is the conversion factor between them. A tiny amount of mass represents an enormous amount of energy, with the speed of light appearing twice in the calculation, magnifying the relationship tremendously. This relationship explains why the sun shines. Deep in the sun's core, hydrogen nuclei fuse together to form helium, and the tiny difference in mass between the original hydrogen and the final helium is converted into energy according to Einstein's equation. The sun converts about 4 million tons of mass into pure energy every second, powering our solar system for billions of years. The speed of light also creates strange effects on simultaneity. Events that appear to happen at the same time for one observer may occur at different times for another observer moving at high speed. There is no universal now that applies everywhere in the universe. Time is relative, and simultaneity depends on your frame of reference. Imagine two lightning strikes occurring simultaneously on opposite ends of a moving train, as observed by someone standing on the platform. To a passenger on the train, these same lightning strikes would not appear simultaneous. The strike toward the front of the train would appear to happen first, followed by the strike toward the rear. Both observers are correct within their own reference frames. This relativity of simultaneity means that the concept of now extends only as far as light can travel. You cannot meaningfully say what is happening right now on a star 10 light-years away, because now is not defined across such distances. The speed of light creates a fundamental limit, not just on motion and energy, but on the very structure of time itself. These insights revolutionized our understanding of gravity as well. Einstein realized that gravity is not a force pulling objects together, but the curvature of space-time itself. Massive objects warp the fabric of space-time, and other objects follow the curved paths through this warped geometry. Light, having no mass, follows the straightest possible path through curved space-time. But even these straight paths appear curved to us when space-time itself is curved. This means that light's path can be bent by gravity, even though light has no mass. Astronomers have observed this effect during solar eclipses, when stars appear slightly displaced from their normal positions because their light is bent as it passes near the sun. This bending of light by gravity creates cosmic lenses, where distant galaxies magnify and distort the images of even more distant objects behind them. The speed of light also determines the structure of space-time around massive objects. Near a black hole, space-time is so severely curved that at a certain distance called the event horizon, not even light can escape. The event horizon is literally the distance from the black hole, where the required escape velocity equals the speed of light. Beyond this point, all paths through space-time lead inexorably inward. As you drift deeper into contemplation, consider that the speed of light is not just a measurement, but a fundamental aspect of reality's architecture. It determines how fast information can travel, how time flows, how space contracts, and how gravity works. It is woven into the very equations that describe electromagnetic fields, quantum mechanics, and the expansion of the universe itself. Every time you look in a mirror, you are seeing yourself as you existed a tiny fraction of a second ago, because light takes time to travel from your face to the mirror and back to your eyes. Every time you have a conversation, there is a minuscule delay as sound waves travel between you and the other person. But light's delay is so small at everyday distances that it creates the illusion of instantaneous communication. Yet this illusion breaks down over cosmic distances. Astronauts on the moon experience a noticeable delay when communicating with Earth. The delay grows longer for more distant space missions. Eventually, as we explore the galaxy, the speed of light will impose fundamental limits on real-time communication across interstellar distances. Einstein's theories showed that the speed of light is not just about light itself, but about the fundamental structure of reality. It is the speed at which space-time allows cause and effect to propagate, the cosmic speed limit that maintains the logical structure of the universe. To truly grasp the implications of relativity, imagine yourself as a passenger on a cosmic journey approaching the speed of light. As your spacecraft accelerates, you would notice nothing unusual inside your cabin. Your watch would tick normally, your coffee would taste the same, and conversations with fellow passengers would proceed normally. This is because all the laws of physics remain consistent within your reference frame. However, if you could somehow observe Earth receding behind you, you would witness extraordinary effects. As your speed increases, you would see Earth's clocks running slower and slower. People would appear to move in slow motion. Entire seasons would pass in what seems like days from your perspective. The faster you travel, the more dramatic this effect becomes. Meanwhile, observers on Earth watching your journey would see the opposite effect. To them, everything aboard your spacecraft would appear to slow down. Your movements would seem sluggish, your clocks would tick slowly, and even the light from your engines would appear shifted toward the red end of the spectrum due to the relativistic Doppler effect. This mutual time dilation reveals something profound about the nature of time itself. Time is not a universal constant flowing at the same rate everywhere. Instead, it is intimately connected to motion and gravity. The speed of light serves as the cosmic mediator that determines how time flows for different observers moving at different speeds. Consider the practical implications of this relationship. Global positioning system satellites orbiting Earth must account for relativistic effects to maintain accuracy. These satellites travel fast enough and experience weak enough gravity compared to Earth's surface that their onboard clocks run slightly faster than identical clocks on the ground. Without corrections for these relativistic effects, GPS coordinates would drift by several miles per day. The speed of light also creates a fundamental asymmetry in how we experience space and time. You can move freely through the three dimensions of space, choosing to go forward, backward, left, right, up, or down, but you cannot choose your movement through time. You are always moving forward through time at the speed of light. This is why physicists sometimes describe massive objects as moving through space-time at the speed of light, with the motion distributed between spatial dimensions and the time dimension. When you sit perfectly still in space, all of your motion through space-time is directed through the time dimension. As you begin to move through space, some of your motion through space-time gets redirected from the time dimension to spatial dimensions. The faster you move through space, the slower you move through time. At the speed of light, all motion would be through spatial dimensions, with no motion through time remaining. This insight helps explain why photons experience no passage of time. From a photon's perspective, it exists simultaneously at all points along its path. The moment of its creation and the moment of its absorption are the same instant. This timeless existence of light particles creates a bridge between past and future, carrying information across vast distances without experiencing duration. The speed of light also establishes fundamental limits on how quickly information can travel through the universe. This creates what physicists call light cones, imaginary cone-shaped regions in spacetime that determine which events can influence each other. Events within your past light cone could have influenced your present moment, while events within your future light cone could potentially be influenced by your present actions. This structure of causality, determined by light speed, prevents logical paradoxes and maintains the orderly flow of cause and effect throughout the universe. Without this cosmic speed limit, effects could precede their causes, creating impossible situations where you could influence your own past or receive information about events before they happen. The relationship between light's speed and gravity reveals another layer of reality's architecture. In Einstein's theory of general relativity, massive objects create curvature in spacetime, and this curvature affects the passage of time. Clocks run slower in stronger gravitational fields, an effect called gravitational time dilation. The speed of light remains constant, but the rate at which time passes changes depending on gravitational strength. This means that time passes slightly slower for someone standing at sea level compared to someone on a mountaintop, because sea level experiences slightly stronger gravity. The effect is incredibly small for everyday situations, but it becomes dramatic near extremely massive objects, like neutron stars or black holes. Near the event horizon of a black hole, gravitational time dilation becomes so extreme that time nearly stops relative to distant observers. If you could somehow survive falling toward a black hole, you would experience time normally, but observers far from the black hole would see you slow down and appear to freeze at the event horizon. Your image red shifted and dimmed until it fades from view. The speed of light also plays a crucial role in the electromagnetic force, one of the fundamental forces of nature. Electric and magnetic fields propagate through space at exactly the speed of light, creating electromagnetic waves. Light itself is simply electromagnetic radiation that happens to be visible to human eyes. The entire electromagnetic spectrum, from radio waves to gamma rays, travels at this same cosmic speed. This connection between light and electromagnetism reveals that the speed of light is not just about optical phenomena, but about the fundamental structure of one of nature's basic forces. The strength of electromagnetic interactions, the behavior of electric charges, and the propagation of magnetic fields are all intimately connected to this cosmic constant. The mathematical elegance of Einstein's equations shows how deeply the speed of light is embedded in the laws of physics. It appears not just in relativity, but in quantum mechanics, electromagnetism, and cosmology. It is truly a universal constant that connects seemingly disparate phenomena under a unified mathematical framework. As you contemplate these deep connections, imagine light not merely as illumination, but as the cosmic messenger that maintains the logical structure of reality. Every photon carries with it the enforcement of causality, ensuring that information cannot travel faster than the speed that maintains the orderly progression of cause and effect. The speed of light emerges as more than a measurement or a limit. It is a fundamental aspect of existence that determines how time flows, how space curves, how forces propagate, and how information travels. It is the speed at which reality itself unfolds, the rate at which the possible becomes actual, the cosmic constant that bridges the gap between what was, what is, and what could be. Imagine for a moment that you could experience existence as a photon of light. This thought experiment takes us into one of the most profound mysteries of physics, where our everyday understanding of time and space completely breaks down. From the perspective of light itself, the universe becomes a place of impossible contradictions and timeless journeys. When a photon is born in the nuclear furnace at the center of the sun, something extraordinary happens. In that instant of creation, from the photon's perspective, it simultaneously exists at every point along its future path. The 8-minute journey to Earth, the moment it enters your eye, and every interaction along the way all happen in the same eternal instant. For light, there is no journey, no duration, no passage of time. This timeless existence of photons reveals something fundamental about the nature of reality. While we experience a world of sequences, of before and after, of causes followed by effects, light exists in a realm where all moments collapse into a single, eternal now. Every photon carries within it the complete story of its existence, from birth to absorption, compressed into what we might call a zero-duration experience. To understand this strange perspective, consider what happens to time as objects approach the speed of light. We have learned that time slows down for fast-moving objects relative to stationary observers. A spacecraft traveling at 90% the speed of light experiences time passing about twice as slowly as observers on Earth. At 99% light speed, time passes 7 times more slowly. At 99.9%, time crawls by at 1/7 the normal rate. As we push closer and closer to light speed, time dilation becomes more and more extreme. At 99.99% of light speed, time passes 100 times more slowly. The mathematical progression continues without limit. At exactly the speed of light, time dilation becomes infinite. Time stops completely. From light's perspective, no time passes at all during its journey across the universe. This creates a paradox that challenges our understanding of existence itself. How can something that experiences no time have a finite speed? How can a photon travel billions of light years across the universe if, from its own perspective, the journey takes no time at all? The answer lies in the strange relationship between space and time at light speed. Just as time contracts to zero for light, so does space. In the direction of a photon's motion, all distances shrink to nothing. The vast emptiness between stars, The enormous scales of galactic space, the incredible distances between galaxy clusters, all compressed to zero length from light's perspective. In the reference frame of a photon, the entire universe in its direction of travel becomes infinitely thin. This means that for light, there is no space to cross and no time in which to cross it. The photon exists simultaneously at its point of origin and its destination. From our perspective, we see light traveling through space over time. But from light's perspective, departure and arrival are the same event. Consider a photon leaving the Andromeda galaxy 2.5 million years ago. From our earthbound perspective, this ancient light has been traveling through the vast emptiness of intergalactic space for eons, crossing distances so enormous that they dwarf human comprehension. But from the photon's perspective, it left Andromeda and arrived at your telescope in the same timeless instant. This creates a profound question about the nature of existence itself. If photons experience no duration, do they truly exist in time as we understand it? Or do they represent something more fundamental, eternal entities that connect different moments in space-time, without themselves being subject to time's flow? The strange perspective of light becomes even more mysterious when we consider photons that have traveled since the early universe. The cosmic microwave background radiation that fills all of space consists of photons that have been traveling for nearly 14 billion years since the universe became transparent to light. These ancient photons carry information about the universe when it was only 380,000 years old, when the first atoms formed and light could finally travel freely through space. From our perspective, these photons have been journeying across an expanding universe for almost the entire history of cosmic time. They have witnessed the formation of the first stars, the birth of galaxies, the evolution of cosmic structure on the largest scales. Yet from their own perspective, they left the hot, dense plasma of the early universe and arrived at our radio telescopes in the same eternal moment. This timeless journey of ancient light suggests that the past is not truly past from light's perspective. The moment of cosmic transparency, when the universe first became clear to light, exists simultaneously with the present moment when we detect these photons. In some sense, the early universe and the present universe are connected by these messengers that experience no passage of time. The perspective of light also illuminates the relationship between observation and reality. When you look at a star, the light entering your eye left that star years ago. You are not seeing the star as it is now, but as it was when the light began its journey. The present state of distant stars is fundamentally unknowable to us, because light takes time to travel across space. But from the photon's perspective, it left the star and entered your eye simultaneously. The star's past state and your present observation are the same event in the photon's timeless reference frame. This suggests that the separation between past and present, between there and here, may be less fundamental than we imagine. Light connects distant places and different times in ways that transcend our ordinary experience of space and time. This connection becomes even more intriguing when we consider that every observation depends on light. You cannot see anything without photons carrying information from the observed object to your eyes. Every measurement, every experiment, every piece of knowledge about the distant universe depends on light's ability to carry information across space and time. Yet each photon that brings us this information exists in a timeless state where all points along its path are simultaneously present. The information that light carries is not transmitted through time in the way we normally think of transmission. Instead, it exists in an eternal state that connects different moments in space-time. The strange perspective of light also affects how we think about the expansion of the universe. Space itself is expanding, carrying distant galaxies away from us at ever-increasing speeds. The most distant observable galaxies are receding from us faster than the speed of light due to the expansion of space itself. Yet the light from these galaxies still reaches us, carrying information about their ancient appearance. From our perspective, this light has been racing across expanding space for billions of years, fighting against the cosmic expansion that stretches its wavelength and dims its intensity. But from the light's perspective, it left these ancient galaxies and arrived at our telescopes in a single, timeless moment, regardless of how space expanded during the journey. This raises profound questions about the relationship between light and the expanding universe. If photons experience no time, how do they interact with the changing geometry of space-time? How does cosmic expansion affect something that exists outside the normal flow of time? The answers hint at even deeper mysteries about the nature of existence. Light may represent a fundamental aspect of reality that transcends the ordinary categories of space and time. It exists at the boundary between the temporal world of massive objects and some more fundamental, timeless realm that underlies physical reality. As you contemplate these mysteries in the quiet moments before sleep, imagine yourself riding alongside a photon on its timeless journey across the cosmos. You would experience the birth and death of stars, the formation and dissolution of galaxies, the entire evolution of the universe, all compressed into a single, eternal moment. In this timeless perspective, every moment of cosmic history exists simultaneously. The Big Bang, the formation of the first atoms, the birth of stars, the emergence of life, and the far future evolution of the universe all coexist in light's eternal now. Perhaps this is what eternity truly means. Not an endless duration, but a timeless state where all moments exist together, outside the flow of time. The perspective of light suggests that our experience of sequential time, of past giving way to present, and present flowing into future, may be an illusion created by our existence as massive beings bound to travel slower than light. From light's perspective, all of time exists simultaneously in an eternal, unchanging present that encompasses the entire history and future of the universe. In the realm of the impossibly small, where atoms dance and particles behave in ways that defy everyday logic, the speed of light takes on new and mysterious roles. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, reveals aspects of light that challenge our understanding of speed, locality, and the very nature of reality itself. At the quantum level, light reveals its dual nature as both wave and particle. This fundamental duality, known as wave-particle duality, shows that light can exhibit properties of waves when we look for wave-like behavior, and properties of particles when we search for particle-like characteristics. This strange behavior suggests that the speed of light may not be as straightforward as it appears in our everyday world. Consider the famous double-slit experiment, one of the most profound demonstrations in all of physics. When we shine light through two parallel slits onto a screen, we observe an interference pattern of bright and dark bands. This pattern can only be explained if light behaves as a wave, with parts of the wave cancelling each other out in some regions and reinforcing each other in others. But here is where quantum mechanics becomes truly mysterious. When we reduce the intensity of light so much that only one photon at a time passes through the apparatus, the interference pattern still appears. Each individual photon somehow passes through both slits simultaneously and interferes with itself. The photon exists in what physicists call a superposition, being in multiple states or locations at the same time. This quantum superposition challenges our understanding of the speed of light. If a single photon passes through both slits simultaneously, what does it mean to say it has a specific speed? The photon appears to travel multiple paths at once, each path potentially requiring different amounts of time to complete. Yet when we detect the photon, we always find it at a specific location at a specific time, as if it had traveled a single, definite path at the speed of light. The act of measurement itself plays a crucial role in quantum mechanics. When we try to determine which slit a photon passes through, by placing a detector near one of the slits, the interference pattern disappears. The photon behaves as if it passed through only one slit, traveling a single path at the speed of light. The very act of observing the photon's path forces it to choose a definite trajectory. This quantum measurement problem raises profound questions about the relationship between observation and reality. Does the photon really travel multiple paths simultaneously when we are not looking, only to collapse into a single path when we observe it? Or does our act of measurement somehow influence the photon's behavior retroactively, determining its path after it has already completed its journey? Even more puzzling is the phenomenon of quantum entanglement, where two or more particles become connected in such a way that measuring one instantly affects the others, regardless of the distance separating them. When two photons are created in an entangled state, measuring the properties of one photon immediately determines the corresponding properties of its partner, even if the partner is on the other side of the galaxy. Einstein famously called this quantum entanglement spooky action at a distance, because it seemed to violate the principle that nothing can travel faster than light. How could information about one photon's measurement instantaneously affect its entangled partner across vast distances? This appeared to create a communication channel that operated faster than light speed, challenging the foundations of relativity. However, careful analysis reveals that quantum entanglement does not actually allow faster than light communication. While the correlations between entangled particles are indeed instantaneous, no usable information can be transmitted through these correlations. The measurement results appear random to observers at each location, and only when the results are compared later, using conventional slower-than-light communication, do the mysterious correlations become apparent. This limitation preserves the cosmic speed limit, while revealing something even more profound about the nature of reality. Quantum entanglement suggests that separateness itself may be an illusion. Entangled particles remain connected at a level deeper than space and time, sharing a unified quantum state that transcends the ordinary boundaries of location and distance. The quantum vacuum, the lowest energy state of space itself, also reveals unexpected connections to the speed of light. Even in empty space, quantum mechanics predicts constant fluctuations where particle-antiparticle pairs spontaneously appear and disappear. These virtual particles, as they are called, exist for such brief moments that they cannot be directly observed, yet their effects can be measured. These quantum fluctuations in the vacuum actually affect the speed of light in subtle ways. Light traveling through the quantum vacuum interacts with virtual particles, causing tiny variations in its speed depending on the energy of the photons and the properties of the vacuum in different regions of space. While these effects are incredibly small, they suggest that the speed of light may not be perfectly constant under all conditions. The quantum nature of light also manifests in phenomena like the photoelectric effect, where light knocks electrons out of metal surfaces. Einstein won the Nobel Prize for explaining this effect by proposing that light consists of discrete packets of energy called photons. The energy of each photon depends on the frequency of the light, not its intensity, showing that light's particle nature is fundamentally quantum mechanical. This quantum description of light reveals that even the concept of light traveling at a specific speed becomes somewhat fuzzy at the quantum level. Photons do not follow definite trajectories like classical particles. Instead, they exist as probability waves that describe the likelihood of finding the photon at different locations and times. The speed of light emerges as an average property of these quantum probability distributions. In quantum field theory, the most sophisticated description of fundamental particles and forces, light emerges as disturbances in the electromagnetic field that permeates all of space. These field fluctuations travel at the speed of light, but the underlying field itself exists everywhere simultaneously. The speed of light becomes the rate at which disturbances propagate through this omnipresent field. This field theoretical perspective suggests that the speed of light may be more accurately understood as the speed of information or causality propagation through the fundamental fields of nature. Light photons are simply one type of disturbance in these fields, but the speed limit applies to all forms of information and causal influence. Quantum mechanics also reveals strange effects near the speed of light itself. As particles with mass are accelerated to higher and higher speeds approaching light speed, their quantum mechanical properties begin to change in dramatic ways. The wavelength of matter waves becomes shorter, quantum tunneling effects become more pronounced, and the boundary between particle and wave behavior becomes increasingly blurred. These relativistic quantum effects suggest that the speed of light represents not just a kinematic limit, but a fundamental boundary in the structure of quantum reality itself. Approaching light speed may reveal new aspects of quantum mechanics that are hidden at lower speeds, possibly opening doorways to deeper levels of physical reality. The quantum Zeno effect provides another intriguing connection between quantum mechanics and the passage of time. This effect occurs when frequent measurements of a quantum system can actually slow down or prevent the system's evolution. By observing a quantum system continuously, we can effectively freeze its development in time, creating a strange form of quantum time control that operates through the measurement process itself. This quantum control of time evolution raises questions about the relationship between consciousness, observation, and the flow of time at the quantum level. If conscious observation can influence the rate at which quantum systems evolve, what does this say about the fundamental nature of time and its connection to awareness and measurement? The uncertainty principle, one of the cornerstones of quantum mechanics, also affects our understanding of light speed. This principle states that we cannot simultaneously know both the exact position and exact momentum of a quantum particle with perfect precision. For photons, this means we cannot determine both their exact location and their exact speed at the same moment. This quantum uncertainty in light's properties suggests that the speed of light, while appearing constant in classical measurements, may exhibit quantum fluctuations that become apparent only when we probe individual photons with extreme precision. The speed of light may not be perfectly defined at the quantum level, existing instead as a probability distribution centered around the classical value. As you drift into contemplation of these quantum mysteries, imagine light not as simple rays traveling through space, but as waves of possibility rippling through the quantum vacuum. Each photon carries within it the potential for multiple realities, multiple paths, multiple speeds, all held in quantum superposition, until the moment of observation collapses these possibilities into a single, definite outcome. In the quantum realm, the speed of light becomes more than a speed limit. It becomes a gateway between the possible and the actual, the speed at which quantum possibilities crystallize into classical reality, the rate at which the universe chooses from among infinite potential futures to create the single timeline we experience as the present moment. For over a century, the speed of light has stood as one of the most sacred constants in physics, unchanging and eternal. Yet as our understanding of the universe deepens and our observations reach further into cosmic time, some scientists have begun to question whether this fundamental constant has truly remained constant throughout the history of the universe. The possibility that the speed of light might vary challenges everything we think we know about reality. If light's speed has changed over cosmic time, then the very foundations of physics would need to be reconsidered. Time, space, energy, and matter would all be affected, potentially rewriting our understanding of how the universe works at its most fundamental level. Consider what such a change would mean for our observations of distant objects. When we look at galaxies billions of light years away, we see them as they existed billions of years ago. If the speed of light was different in the early universe, then our calculations of distances, ages, and the expansion rate of the universe could all be wrong. The cosmic timeline itself might need to be completely revised. The first hints that physical constants might not be truly constant came from detailed studies of ancient light from distant quasars. These incredibly bright objects, powered by supermassive black holes, shine so brilliantly that they can be observed across most of the visible universe. The light from the most distant quasars has been traveling for over 10 billion years, carrying information about the physical conditions when the universe was much younger. When astronomers carefully analyzed the spectrum of light from these distant quasars, they discovered something unexpected. The fine structure constant, a fundamental number that determines the strength of electromagnetic interactions, appeared to be slightly different in the early universe compared to its value today. This discovery sent shockwaves through the physics community, because if one fundamental constant could change, perhaps others could as well. The fine structure constant is intimately connected to the speed of light through the basic equations of electromagnetism. If this constant has changed over cosmic time, it could indicate that the speed of light itself has varied. Some theoretical models suggest that in the very early universe, when temperatures and energies were far higher than anything we can reproduce in laboratories today, the speed of light might have been dramatically different from its current value. One such theory proposes that in the first moments after the Big Bang, the speed of light was much higher than it is today. This varying speed of light cosmology attempts to solve some puzzling problems in our current understanding of the early universe, particularly the horizon problem and the flatness problem that plague standard cosmological models. The horizon problem arises from the observation that the cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature in all directions across the sky. This uniformity is puzzling because regions of the sky that are now separated by vast distances could never have been in contact with each other if light has always traveled at its current speed. How could they reach thermal equilibrium if they could never exchange information? If the speed of light was much higher in the early universe, these distant regions could have been in causal contact, allowing them to reach the same temperature before the speed of light decreased to its current value. This varying speed of light could provide a natural explanation for the observed uniformity of the cosmic microwave background without requiring the exotic physics of cosmic inflation. The flatness problem concerns the observation that the geometry of space appears to be remarkably close to perfectly flat on large scales. In standard cosmology, this flatness requires the initial conditions of the universe to be fine-tuned to extraordinary precision. If the speed of light was different in the early universe, the dynamics of cosmic expansion could naturally drive space toward flatness without requiring such precise initial conditions. These varying speed of light theories remain highly speculative, but they illustrate how changes in this fundamental constant could profoundly affect our understanding of cosmic evolution. If light speed has decreased over time, it would mean that the early universe was a very different place, with different physical laws governing the behavior of matter and energy. Laboratory experiments have also searched for possible variations in the speed of light over much shorter timescales. Some researchers have claimed to detect tiny fluctuations in light speed that correlate with Earth's motion through space or with the gravitational fields of the Sun and Moon. While these claims remain controversial and have not been definitively confirmed, they suggest that even small variations in light speed might be detectable with sufficiently precise measurements. The possibility of varying light speed also connects to theories of extra dimensions and string theory. In these advanced theoretical frameworks, our familiar three-dimensional space may be embedded in a higher dimensional realm, where the fundamental constants we observe are determined by the geometry and dynamics of these extra dimensions. Changes in the extra-dimensional structure could cause apparent variations in the speed of light and other constants in our three-dimensional slice of reality. Some string theory models predict that the values of fundamental constants should vary across different regions of a vast multiverse, with each region having its own set of physical laws. In such scenarios, the speed of light that we observe might be just one possible value among many, selected by the particular conditions that allowed life to emerge in our cosmic neighborhood. The relationship between the speed of light and other fundamental constants also raises intriguing questions about the nature of physical law. The speed of light appears in equations throughout physics, from electromagnetism to quantum mechanics to general relativity. If it varies, then all of these theories would need to be modified in consistent ways to maintain their mathematical coherence. Consider how a changing speed of light would affect the relationship between energy and mass through Einstein's famous equation. If the speed of light was higher in the past, then the same amount of mass would correspond to more energy, potentially affecting the rates of nuclear reactions in stars and the synthesis of heavy elements in the early universe. The abundance of elements we observe today might reflect not just the nuclear physics of stellar cores, but also the historical evolution of fundamental constants. The speed of light also determines the rate at which electromagnetic fields propagate through space. If this speed has changed, it would affect how charged particles interact with each other and how electromagnetic radiation travels through the universe. The behavior of atoms, molecules, and larger structures could all be subtly different if the speed of light was not constant throughout cosmic history. Modern theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, often predict that space and time themselves have a discrete, granular structure at the smallest scales. In such theories, the speed of light might not be perfectly constant, but could fluctuate slightly due to the quantum foam that makes up the fabric of spacetime itself. These quantum fluctuations in spacetime geometry could cause tiny variations in light speed that depend on the energy of the photons and the local conditions of the vacuum. While such effects would be incredibly small, they might be detectable in precision experiments or in observations of high-energy photons from distant astronomical sources. The search for varying fundamental constants has led to increasingly sophisticated observational techniques. Astronomers now analyze the light from distant objects with unprecedented precision, looking for tiny shifts in spectral lines that could reveal changes in the fine structure, constant, or other fundamental parameters. These observations probe the consistency of physical law across vast distances and cosmic times. Some of the most precise tests come from studies of natural nuclear reactors that operated in ancient uranium deposits billions of years ago. By analyzing the isotopic ratios left behind by these natural reactors, scientists can determine whether the rates of nuclear reactions were different in the past, which could indicate changes in fundamental constants, including those related to the speed of light. The possibility that the speed of light might vary also raises profound philosophical questions about the nature of natural law. We often think of physical constants as eternal and unchanging, reflecting deep truths about the structure of reality. But if these constants can evolve over time, it suggests that even our most fundamental laws of physics might be temporary features of the current cosmic epoch. Perhaps the constants we observe today are more like the current weather conditions in the universe, temporary states in an ongoing evolution of physical law that stretches across cosmic timescales. The speed of light that seems so fundamental to us might be just a snapshot of a dynamic quantity that has been changing since the beginning of time. As you contemplate these possibilities in the quiet moments before sleep, imagine the speed of light not as a rigid barrier, but as a flowing river whose current has varied throughout cosmic history. In the turbulent early moments of the universe, this river might have rushed at torrential speeds, slowing to its current measured pace as the cosmos aged and cooled. This evolving speed of light could mean that the universe is far stranger and more dynamic than we imagine, with the very foundations of physics shifting beneath us, like continental drift on the grandest possible scale. The constants that define reality might themselves be part of a cosmic evolution, changing and adapting as the universe grows older and more complex. If the speed of light is not truly constant, then every measurement we make, every theory we construct, and every conclusion we draw about the nature of reality carries within it the implicit assumption that we live in a particular moment of cosmic history. The physics we discover might be the physics of our current cosmic epoch, valid for now but potentially different from the physics that governed the early universe or that will govern the far future. The question of whether the speed of light is constant touches the very heart of what it means to do science in a dynamic, evolving universe where even the most fundamental aspects of reality might be subject to change across cosmic time. Throughout human history, every seemingly insurmountable barrier has eventually been crossed. We learned to fly when flight seemed impossible, we split the atom when atoms were thought indivisible, and we reached the moon when space travel existed only in dreams. Now we face perhaps the ultimate barrier, the speed of light itself. Could this cosmic speed limit, so fundamental to our understanding of physics, eventually be surpassed? The question challenges not just our technology, but our very conception of what is possible in this universe. Einstein's special relativity seems to forbid faster than light travel absolutely, showing that accelerating any object with mass to light speed would require infinite energy. Yet theoretical physicists have discovered intriguing loopholes and exotic possibilities that might, under extraordinary circumstances, allow information, or even matter, to effectively travel faster than light. Consider first the theoretical particles known as tachyons, hypothetical entities that would always travel faster than light. The name comes from the Greek word for swift, and these particles represent a strange mirror image of ordinary matter. While normal particles require energy to speed up and approach light speed, tachyons would require energy to slow down and approach light speed from above. In the mathematical framework of relativity, tachyons would have imaginary mass, a concept that sounds absurd but emerges naturally from the equations when speeds exceed light. For tachyons, light speed would represent an impenetrable barrier from above, just as it represents an impenetrable barrier from below for ordinary matter. Tachyons could never slow down to light speed, just as we could never speed up to light speed. If tachyons exist, they would create a strange universe where causality could be violated. A tachyon signal sent from Earth could potentially arrive at its destination before it was sent, creating the possibility of receiving messages from the future. Such violations of causality would lead to logical paradoxes, which is one reason why most physicists suspect that tachyons do not actually exist in nature. However, the mathematical consistency of tachyon theories keeps them alive as theoretical possibilities. Some interpretations of quantum field theory suggest that tachyonic fields might exist in certain unstable quantum states, though these would quickly decay into ordinary, slower-than-light particles. The very instability that prevents stable tachyons might be nature's way of preserving causality. More promising for potential faster-than-light travel are exotic solutions to Einstein's equations that allow space itself to move faster than light. While matter cannot exceed light speed through space, space itself is not bound by this limitation. The expansion of the universe already carries distant galaxies away from us faster than light, demonstrating that space can exceed this cosmic speed limit. The Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994, exploits this property of space to create a theoretical faster-than-light propulsion system. The concept involves contracting space in front of a spacecraft while expanding space behind it, creating a bubble of warped space-time that carries the ship along faster than light, while the ship itself remains stationary within the bubble. Imagine riding inside such a warp bubble. From your perspective, you would feel no acceleration and experience no time dilation. You would remain in a region of flat, normal space-time, while the universe rushes past outside your bubble. The journey to nearby stars that would take thousands of years at conventional speeds could potentially be completed in months or years within a warp bubble. However, the Alcubierre drive requires exotic matter with negative energy density to create the necessary space-time curvature. Such matter would need to have properties unlike anything we have ever observed, with gravitational effects opposite to normal matter. Instead of attracting other matter, negative energy density would create gravitational repulsion, pushing space-time apart rather than pulling it together. The total amount of negative energy required for an Alcubierre drive would be enormous, possibly equivalent to the mass energy of entire stars. Even if such exotic matter exists, concentrating these vast energies into the precise configuration needed for warp drive would represent a technological challenge far beyond our current capabilities. Some researchers have proposed modifications to the Alcubierre design that might reduce the energy requirements, but even the most optimistic estimates still require exotic physics and energy sources that remain purely theoretical. The practical construction of a warp drive, if possible at all, would likely require scientific advances that we cannot yet imagine. Wormholes represent another theoretical pathway to faster-than-light travel, though they operate on different principles than warp drives. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing travel between them without crossing the intervening space. A wormhole linking Earth to a star 20 light-years away could potentially allow nearly instantaneous travel between these locations. The concept of traversable wormholes emerges from solutions to Einstein's field equations, showing that such structures are mathematically possible within the framework of general relativity. However, like warp drives, stable traversable wormholes would require exotic matter to prevent them from collapsing immediately after formation. Natural wormholes, if they exist, would likely be microscopic and incredibly unstable, lasting for tiny fractions of a second before collapsing. Creating or maintaining a wormhole large enough for human travel would require the same type of negative energy density needed for warp drives, placing this technology in the realm of highly speculative future science. Even if traversable wormholes could be created, they would raise complex questions about causality and time travel. A wormhole could potentially connect not just distant locations, but different moments in time, allowing travelers to arrive at their destination before they departed. Such closed time-like curves would create the same causality paradoxes associated with tachyons. Some theoretical physicists have proposed that the laws of physics might contain built-in protections against causality violations, automatically preventing the formation of any structure that could enable time travel. This chronology protection conjecture suggests that nature itself conspires to preserve the logical order of cause and effect. Quantum mechanics introduces additional possibilities for apparent faster-than-light phenomena. Quantum tunneling allows particles to pass through energy barriers that would be impossible to cross according to classical physics. While the tunneling process itself does not exceed light speed, some interpretations suggest that the time required for tunneling could be effectively zero, allowing particles to appear on the other side of a barrier instantaneously. This quantum tunneling time has been the subject of intense debate among physicists. Experiments with photons tunneling through barriers have produced results that seem to suggest faster than light transit times, though these measurements remain controversial and may not represent true faster than light information transfer. The phenomenon of quantum entanglement, which we explored earlier, creates correlations between distant particles that appear instantaneous, regardless of separation. While this does not allow faster than light communication, it does demonstrate that quantum mechanical relationships can transcend the normal limitations of space and time in ways that classical physics cannot explain. Some researchers have speculated about quantum communication protocols that might exploit entanglement to achieve faster than light information transfer, but all known proposals run afoul of the no communication theorem, which proves that quantum entanglement cannot be used to send usable information faster than light. The quantum correlations are real and instantaneous, but they cannot be controlled in ways that would allow practical communication. The expansion of space itself offers another perspective on faster than light motion. During the inflationary epoch, immediately after the Big Bang, space expanded at rates far exceeding the speed of light, carrying matter and energy along with it. This cosmic inflation demonstrates that faster than light motion is not only possible, but may have been a fundamental feature of the very early universe. If the mechanisms that drove cosmic inflation could be understood and controlled, they might provide a pathway to faster than light travel that does not violate the principles of relativity. Such technology would essentially recreate the conditions of the early universe on a local scale, using the same physics that stretched space during inflation to transport matter across vast distances. Recent advances in our understanding of dark energy, the mysterious force driving the current acceleration of cosmic expansion, might also provide clues about manipulating space-time for faster than light travel. If dark energy can be harnessed or controlled, it might be possible to create localized regions of accelerated expansion that could serve as natural warp drives. However, our current understanding of dark energy remains extremely limited. We know that it constitutes about 70% of the universe's total energy content, but we have no clear idea what it actually is or how it operates. Developing technology based on dark energy would require fundamental breakthroughs in our understanding of this cosmic mystery. Alternative theories of gravity and space-time also suggest possible routes to faster than light travel. Some proposals for modified gravity theories, or extra-dimensional physics, predict phenomena that could enable apparent faster than light motion without violating the fundamental principles of causality. String theory, with its prediction of additional spatial dimensions beyond the familiar three, offers the possibility that our universe is a three-dimensional membrane embedded in a higher dimensional space. Travel through these extra dimensions might allow shortcuts between distant points in our familiar three-dimensional space, effectively enabling faster than light travel from our perspective. However, if extra dimensions exist, they are either incredibly small or somehow hidden from our normal experience. Accessing these dimensions for travel would require technology capable of manipulating the fundamental structure of space-time itself, representing a level of advancement that far exceeds our current scientific capabilities. The search for faster-than-light phenomena continues in particle accelerators, where scientists study the behavior of matter under extreme conditions. While no confirmed faster-than-light particles have been discovered, some experimental results have suggested the possibility of subtle violations of light speed limits under very specific circumstances. These experimental hints remain controversial and have generally been explained within the framework of conventional physics, but they keep alive the possibility that our understanding of the speed limit is incomplete. Future experiments with more powerful accelerators and more sensitive detectors might reveal new phenomena that challenge our current understanding of light speed limits. As you drift into contemplation of these possibilities, imagine a future where the barriers we consider absolute today have become merely historical curiosities. Perhaps advanced civilizations have learned to fold space, manipulate time, or access dimensions beyond our current perception, making faster than light travel as commonplace as air travel is to us today. The universe might be far more connected than we realize, with hidden pathways and shortcuts that could transform our understanding of distance and isolation. The galaxies that seem impossibly remote might be linked by networks of traversable wormholes or accessible through manipulation of space itself. Yet even if faster than light travel proves forever impossible for material objects, the mere contemplation of these possibilities expands our conception of what might be achievable through deep understanding of the fundamental laws of nature. The speed of light barrier, rather than being an eternal prison, might be a puzzle waiting to be solved by future generations who see deeper into the mysteries of existence than we can imagine today. Time flows around us like an invisible river, carrying us from past to future in what seems like an unchangeable current. We experience time as linear, sequential, and absolute. Yet modern physics reveals that time is far stranger than our everyday experience suggests. The speed of light plays a central role in this strangeness, acting as the key that unlocks the deepest mysteries of temporal reality and reveals that time itself might be the grandest illusion of all. Einstein's revolutionary insight was that time is not universal. What seems like a single, shared moment to one observer becomes a collection of different moments spread across space for another observer moving at high speed. This relativity of simultaneity shows that there is no universal now, no cosmic moment that defines the present for the entire universe. Instead, the present is personal, defined by your particular motion through space-time. Imagine two events occurring simultaneously in your reference frame, perhaps two lightning strikes hitting opposite ends of a field at the exact same moment. To someone traveling past you at high speed, these same events would not appear simultaneous. One strike would seem to occur before the other, with the time difference depending on the observer's velocity. The faster the observer moves, the greater the time separation between events that you perceive as simultaneous. This relativity of time creates what physicists call the block universe, a four-dimensional structure where all moments in time exist simultaneously. Past, present, and future are all equally real, like different locations along a spatial dimension. Your perception of moving through time from past to future is similar to your perception of moving through space from one location to another. Time becomes a landscape that you traverse, rather than a river that carries you along. In this block universe view, the speed of light determines the structure of causality. Events can only influence each other if they are connected by light signals or slower moving influences. This creates light cones, imaginary cone-shaped regions in space-time that define which events can affect which other events. The speed of light becomes the speed of causality itself, the rate at which cause and effect can propagate through the four-dimensional fabric of space-time. Consider the implications of this causal structure. Events outside your past light cone could not have influenced your current moment, while events outside your future light cone cannot be influenced by your current actions. The speed of light creates a fundamental limitation, not just on communication, but on the very possibility of causal connection between events separated in space and time. This causal structure raises profound questions about free will and determinism. If all moments in time are equally real in the block universe, then the future already exists in the same sense that distant locations already exist. Your future actions are already part of the four-dimensional structure of space-time, raising questions about whether you truly have the freedom to choose your path through time. Yet the light cone structure preserves a form of causal freedom. While the future may already exist in some sense, it cannot influence the present because causal influences cannot travel faster than light. Your choices in the present moment are not determined by future events, even if those future events already exist in the block universe. The speed of light creates a causal barrier that protects the present from influence by the future. The concept of time travel brings these temporal mysteries into sharp focus. If time is truly like a spatial dimension in the block universe, then travel to the past should be theoretically possible, just as travel to distant locations is possible. The speed of light plays a crucial role in most time travel scenarios, either as a barrier to be overcome or as the mechanism that enables temporal journeys. Closed time-like curves represent the most general description of time travel in relativity theory. These are paths through space-time that loop back to earlier times, allowing an object to return to its own past. Such curves could theoretically exist near extremely massive rotating objects, in traversable wormholes, or in regions where space-time is severely distorted by exotic matter. However, closed time-like curves create logical paradoxes that challenge our understanding of causality. The grandfather paradox asks what happens if you travel to the past and prevent your own grandfather from meeting your grandmother. If your grandparents never meet, you are never born, so you cannot travel to the past to prevent their meeting. This creates a logical contradiction that seems to make time travel impossible. Some physicists have proposed solutions to these paradoxes that preserve both time travel and logical consistency. The many worlds interpretation of quantum mechanics suggests that time travel creates alternate timelines rather than changing the original past. When you travel to the past, you create a new branch of reality where events unfold differently, while your original timeline remains unchanged. Another proposed solution is the self-consistency principle, which suggests that the laws of physics conspire to ensure that time travelers can only cause events that were already part of history. Any attempt to change the past would be automatically thwarted by circumstances that preserve the original timeline. The universe becomes self-healing, automatically correcting any potential paradoxes. The speed of light also plays a role in more exotic time travel scenarios. Some theoretical proposals involve accelerating matter to speeds very close to light speed and using time dilation effects to travel to the future. While this is not time travel in the science fiction sense, it would allow you to experience less time while more time passes in the outside world, effectively jumping into the future. Consider a journey to a star 10 light-years away at 99.9% the speed of light. The round trip would take over 20 years as measured by observers on Earth, but due to time dilation, you would experience only about 10 months during the journey. You would return to an Earth that has aged 20 years while you have aged less than a year, effectively traveling into Earth's future. This type of time travel to the future is theoretically possible and does not create logical paradoxes. However, it is a one-way journey. There is no known way to return to your original time once you have jumped into the future through relativistic time dilation. The speed of light allows forward time travel, but seems to forbid backward time travel. Quantum mechanics adds another layer of strangeness to our understanding of time and its relationship to light speed. The quantum measurement process appears to involve a fundamental irreversibility that defines the arrow of time. When quantum systems collapse from superposition states into definite outcomes, they create an asymmetry between past and future that might be responsible for our perception of time's direction. The speed of light limits how quickly information about quantum measurements can propagate through space. This creates a cosmic censorship of quantum events, ensuring that the effects of quantum measurements cannot influence events outside their light cones. The quantum arrow of time and the relativistic structure of causality work together to maintain the logical consistency of physical law. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the collapse of quantum states and the creation of definite outcomes from quantum possibilities. If consciousness is responsible for the transition from quantum possibility to classical reality, then the speed of light might determine how quickly conscious observation can influence the fabric of reality itself. This connection between consciousness, quantum mechanics, and the speed of light raises profound questions about the nature of time and awareness. Perhaps our perception of time's flow is not just an illusion, but an active process of consciousness collapsing quantum possibilities into definite realities at the speed of light. Time might flow because consciousness flows, creating a moving boundary between the determined past and the undetermined future. The relationship between time and the speed of light also appears in cosmological contexts. The expansion of the universe creates a cosmic time that defines the age and evolution of the cosmos. This cosmic time is intimately connected to the speed of light through the equations that govern cosmic expansion and the propagation of information across cosmic scales. The observable universe is defined by the distance that light has traveled since the Big Bang, creating a horizon beyond which we cannot see. This cosmic horizon is not a fixed boundary in space, but a moving frontier that expands as light from more distant regions has time to reach us. The speed of light determines the size and evolution of the observable universe, linking the cosmic timescale to the fundamental speed of causality. Dark energy, the mysterious force driving the acceleration of cosmic expansion, might also be connected to the nature of time and the speed of light. Some theories suggest that dark energy represents a fundamental property of space-time itself, a cosmic tension that drives the expansion of the universe and might influence the flow of time on cosmic scales. If dark energy affects the rate at which time passes in different regions of the universe, then cosmic expansion might involve not just the stretching of space, but the acceleration or deceleration of time itself. The speed of light would remain constant within any local region, but the rate at which time flows could vary across cosmic distances. creating a complex temporal landscape that connects the local flow of time to the global evolution of the universe. The holographic principle, emerging from studies of black holes and quantum gravity, suggests that all the information in a volume of space can be encoded on its boundary surface. This principle implies that time might be an emergent property that arises from more fundamental information processing at the boundary of space-time regions. The speed of light would then represent the rate at which information can be processed and transmitted across these holographic boundaries. In this holographic view, time becomes a measure of information flow rather than a fundamental dimension of reality. The passage of time corresponds to the processing of information encoded on space-time boundaries, with the speed of light determining the maximum rate of this cosmic computation. Our perception of temporal flow might reflect our participation in this universal information processing system. As you drift into contemplation of these temporal mysteries, imagine time not as a flowing river, but as a vast ocean where past, present, and future coexist like different depths of water. The speed of light creates currents in this temporal ocean, determining how events at different depths can influence each other and creating the structure of causality that maintains the logical consistency of existence. Perhaps our experience of moving through time is like swimming through this temporal ocean, with consciousness creating a wake of collapsed quantum possibilities behind us and a bow wave of potential futures ahead. The speed of light determines how far our influence can reach through this ocean of time, creating boundaries that protect causality while allowing for the rich complexity of temporal experience. The illusion of time might not be that time is unreal, but that our perception of time as linear and absolute is incomplete. Time might be far richer and more complex than we imagine, with the speed of light serving as our guide to its deeper mysteries. In understanding light's role in the structure of time, we might be approaching the key to unlocking the greatest illusion of all, the separation between past, present, and future that defines our everyday experience of existence. In the vast theater of the cosmos, light serves as both messenger and architect, carrying information across impossible distances, while simultaneously shaping the very structure of the universe we observe. The speed of light does not merely define how fast electromagnetic radiation travels through space, it fundamentally determines what we can know about the cosmos and how cosmic structure itself evolves over time. Every observation we make of the universe beyond our immediate vicinity depends entirely on light that has traveled from distant sources to our telescopes and detectors. When we look up at the night sky, we are not seeing the universe as it is now, but as it was when the light we observe began its journey toward us. The speed of light transforms every astronomical observation into an act of time travel, allowing us to peer directly into the cosmic past. Consider the nearest star visible to the naked eye, Proxima Centauri, whose light takes 4 years and 3 months to reach Earth. When you glimpse this faint red star in the night sky, you are seeing it as it existed over 4 years ago. If Proxima Centauri were to suddenly explode in a supernova today, we would continue to see it shining peacefully for more than 4 years before the flash of the explosion reached our telescopes. This light travel time effect becomes more dramatic as we observe more distant objects. The beautiful Andromeda galaxy, visible as a faint smudge to the naked eye, appears to us as it existed 2.5 million years ago. The light now entering our eyes left Andromeda when early human ancestors were first learning to use stone tools. We are witnessing an ancient galaxy, preserved in light and delivered across the vast emptiness of intergalactic space. The speed of light creates what astronomers call the observable universe, a spherical region centered on Earth, beyond which we cannot see because light from more distant objects has not yet had time to reach us. This cosmic horizon is not a physical boundary, but a limitation imposed by the finite speed of light and the finite age of the universe. The observable universe has a radius of approximately 46 billion light-years, though this distance is larger than the age of the universe in years, because space itself has been expanding during the light travel time. Beyond this cosmic horizon lies the unobservable universe, regions of space that remain forever hidden from our direct view, not because of technological limitations, but because light from these distant realms has not yet had time to cross the expanding cosmos. The speed of light creates a fundamental boundary to astronomical observation that cannot be overcome by building larger telescopes or more sensitive detectors. The relationship between light speed and cosmic expansion creates a complex interplay that shapes our understanding of cosmic structure and evolution. As the universe expands, the wavelength of light traveling through space gets stretched, causing distant objects to appear redder than they would if space was static. This cosmological redshift allows astronomers to measure how fast distant galaxies are receding from us, and to determine the expansion rate of the universe itself. The speed of light also determines the rate at which information about cosmic events can propagate through the universe. When a massive star explodes in a supernova, the light from the explosion can only spread outward at light speed, creating an expanding sphere of illumination that gradually encompasses larger and larger regions of space. Civilizations at different distances from the supernova would learn about the explosion at different times, determined by how long light takes to travel from the explosion site to their location. This finite speed of information propagation has profound implications for our understanding of cosmic causality. Events that occur in different parts of the universe cannot influence each other if they are separated by distances greater than light can travel in the time available. This creates a cosmic web of causal connections and separations that determines which events can be connected by cause and effect relationships. The cosmic microwave background radiation provides a remarkable example of how light preserves and delivers information about the early universe. This faint radiation, detected in all directions across the sky, consists of photons that have been traveling through space for nearly 14 billion years. These ancient photons carry information about the universe when it was only 390,000 years old, when it first became transparent to light. From the perspective of these cosmic microwave background photons, they left the hot, dense plasma of the early universe and arrived at our radio telescopes in the same timeless instant. Yet from our perspective, they have been journeying across an expanding cosmos for nearly the entire history of time, carrying within them the fossil evidence of cosmic conditions billions of years before the Earth was formed. The speed of light also plays a crucial role in the formation and evolution of cosmic structure. Gravity, which shapes the large-scale structure of the universe, propagates at the speed of light, according to Einstein's general relativity. This means that gravitational influences between distant objects are delayed by light travel time, just like electromagnetic signals. When two massive objects orbit each other, such as a pair of neutron stars, they lose energy by emitting gravitational waves that propagate outward at the speed of light. This energy loss causes the orbit to gradually shrink, eventually leading the objects to spiral together and merge in a cataclysmic collision. The gravitational waves from such events carry information about the collision across cosmic distances, allowing us to study these extreme phenomena through gravitational wave astronomy. The finite speed of light also affects how cosmic structure grows and evolves over time. In the early universe, regions of space that are now widely separated were once close enough to exchange information and reach thermal equilibrium. As the universe expanded, these regions were carried apart faster than light could travel between them, freezing in place the conditions that existed when they were last in causal contact. This causal horizon effect helps explain why the cosmic microwave background appears so uniform across the sky. Regions of the early universe that are now separated by vast distances were once close enough to exchange energy and reach the same temperature. The uniformity we observe today is a fossil remnant of this early causal contact, preserved across cosmic time by the finite speed of light. The speed of light also determines the rate at which we can gather information about cosmic evolution. Each year, the cosmic horizon expands by 1 light year, allowing us to see slightly further into the universe and slightly further back in cosmic time. New regions of space gradually come into view as light from increasingly distant sources has time to reach our telescopes. This means that our view of the universe is constantly evolving, not just because we build better instruments, but because the cosmos itself is revealing new information as light from previously invisible regions finally arrives at Earth. The speed of light creates a natural rate of cosmic revelation that cannot be accelerated by technological advancement. The interaction between light and matter throughout cosmic history has also shaped the evolution of the universe in fundamental ways. During the epoch of reionization, roughly 1 billion years after the Big Bang, the first stars and galaxies began to shine, filling the universe with ultraviolet radiation that ionized the neutral hydrogen gas pervading space. This transformation from a neutral to an ionized universe fundamentally changed how light could propagate through space. Before reionization, the universe was opaque to many forms of radiation, limiting how far light could travel before being absorbed by neutral gas. After reionization, space became largely transparent, allowing light to travel vast distances without obstruction. This transition marked a fundamental change in the cosmic role of light, transforming it from a localized phenomenon to a truly cosmic messenger. The speed of light also determines the timescales on which cosmic feedback processes operate. When massive stars form in a galaxy, their intense radiation and stellar winds affect the surrounding gas, potentially triggering or suppressing the formation of additional stars. These feedback effects propagate outward at the speed of light, creating expanding regions of influence that shape galactic evolution over millions of years. Similarly, when supermassive black holes at the centers of galaxies become active, they can produce jets of high-energy particles and intense radiation that affect the entire galaxy. These active galactic nuclei create expanding bubbles of influence that propagate at light speed, regulating star formation and gas dynamics across vast regions of space. The cosmic distance ladder, the series of techniques astronomers use to measure distances to increasingly remote objects, is fundamentally based on observations of light from standard candles, objects whose intrinsic brightness is known. Type Ia supernovae, which have remarkably consistent peak brightness, serve as cosmic lighthouses that allow astronomers to measure distances across billions of light years. The speed of light enters these distance measurements in multiple ways. The light travel time to distant supernovae tells us how long ago they exploded, while the observed brightness tells us how far away they were when the explosion occurred. The cosmological redshift of the supernova light reveals how much the universe has expanded during the light travel time, allowing astronomers to trace the history of cosmic expansion. These observations led to the discovery of dark energy, the mysterious force driving the accelerating expansion of the universe. The speed of light serves as the cosmic postal service that delivers this information about cosmic acceleration across billions of years of cosmic time, allowing us to study the large-scale dynamics of space-time itself. The role of light in cosmic evolution extends beyond simple information transport to fundamental thermodynamic processes that shape the universe. The cosmic radiation background, including both the cosmic microwave background and various other radiation fields, provides a thermal reservoir that affects the temperature and energy balance of matter throughout the universe. As the universe expands and cools, this background radiation shifts to longer wavelengths and lower energies, driving a cosmic cooling process that affects everything from the formation of the first atoms to the thermal evolution of interstellar gas. The speed of light determines how quickly this thermal information can propagate through space, setting the pace of cosmic thermodynamic evolution. As you drift into contemplation of light's cosmic role, imagine the universe as a vast symphony where light serves as both the musical notes and the medium through which the music travels. Every star, galaxy, and cosmic event contributes its voice to this cosmic composition, with light carrying the music across space and time to create the magnificent harmony we observe in the night sky. The speed of light becomes the tempo of this cosmic symphony, determining how quickly themes and variations can spread from one part of the universe to another. The symphony we hear today contains echoes from the distant past, harmonies that began billions of years ago and are only now reaching our cosmic location. In this grand performance, we are both audience and participant, observing the cosmic symphony while contributing our own small voice to its ongoing evolution. The speed of light ensures that our cosmic voice, like all others, will someday reach distant observers, carrying information about our corner of the universe across the vast expanses of space and time. The question of whether we can observe or interact with phenomena beyond the speed of light pushes us to the very frontiers of human imagination and scientific possibility. While Einstein's relativity seems to create an absolute barrier at light speed, the ingenuity of human thought continues to explore whether this cosmic speed limit might be circumvented through indirect means, exotic technologies, or entirely new forms of observation that transcend our current understanding of physics. Consider first the remarkable fact that we already observe phenomena that appear to move faster than light in certain contexts. The shadows cast by objects near a light source can sweep across distant surfaces faster than light speed. If you shine a flashlight at the moon and quickly move the beam across its surface, the spot of light can race across the lunar landscape, at many times the speed of light. However, this apparent faster-than-light motion is illusory because no information or energy actually travels at the speed of the moving spot. Similarly, phase velocities in certain materials can exceed the speed of light. When light passes through specially prepared atomic gases under specific conditions, the peak of a light pulse can appear to exit the material before it fully enters, creating the illusion of faster-than-light propagation. These experiments demonstrate that the concept of light speed is more subtle than our everyday experience suggests, with different aspects of a light wave potentially traveling at different speeds. These phenomena reveal that the speed of light barrier applies specifically to the transmission of information and energy, not to all forms of apparent motion. This distinction opens intriguing possibilities for observing faster-than-light effects without violating the fundamental principles of relativity. We might be able to witness the consequences of faster-than-light phenomena without directly observing the phenomena themselves. Gravitational wave astronomy represents one of our most promising tools for potentially observing signatures of exotic physics that might involve faster-than-light phenomena. Gravitational waves propagate at the speed of light, but they can be generated by events involving matter moving at significant fractions of light speed, or by exotic objects whose behavior might reveal physics beyond our current understanding. When neutron stars spiral together before merging, they reach orbital velocities approaching the speed of light in their final moments. The gravitational waves produced by these extreme events carry information about physics in the strongest gravitational fields and highest energy densities accessible to observation. If exotic, faster-than-light phenomena occur in such extreme environments, their signatures might be detectable in the gravitational wave signals. Black holes, those mysterious regions where gravity becomes so strong that not even light can escape, provide another potential window into physics beyond the speed of light barrier. The event horizon of a black hole is precisely defined as the distance where the escape velocity equals the speed of light. But what happens to information that falls past this boundary? The black hole information paradox suggests that information cannot be destroyed, even when it falls into a black hole. Some proposed solutions to this paradox involve faster-than-light communication between the black hole interior and exterior, or the existence of shortcuts through space-time that could allow information to escape faster than light could travel around the black hole. Hawking radiation, the theoretical emission of particles from black holes due to quantum effects near the event horizon, might carry information about the black hole's interior in ways that transcend normal speed of light limitations. Recent theoretical work suggests that quantum entanglement between particles inside and outside the black hole could create information transfer mechanisms that operate faster than classical light speed, while still respecting the fundamental principles of quantum mechanics. The study of quantum entanglement itself offers another avenue for potentially observing faster-than-light correlations. While quantum entanglement cannot be used to send usable information faster than light, the correlations themselves are instantaneous across any distance. Advanced quantum technologies might allow us to exploit these correlations to observe phenomena that would otherwise be hidden by light speed limitations. Imagine a network of quantum entangled particles distributed across vast distances throughout the galaxy. Changes in quantum states at one location would immediately create correlated changes at all other locations, potentially allowing the observation of cosmic events before light from those events could travel through normal space. While this would not enable faster-than-light communication, it might provide a form of faster-than-light sensing or correlation detection. Cosmic inflation, the rapid expansion of space during the first fraction of a second after the Big Bang, demonstrates that space itself can expand faster than light. During inflation, regions of space that were initially in causal contact were carried apart faster than light could travel between them, effectively breaking the causal connections that had previously existed. If we could understand and harness the mechanisms that drove cosmic inflation, we might be able to create controlled regions of faster than light space expansion. Such technology could potentially allow us to observe distant regions of the universe by bringing them closer to us through space contraction, rather than waiting for light to travel the vast distances involved. Advanced propulsion concepts based on manipulating space-time might also enable forms of observation that effectively transcend light speed limitations. The Alcubierre warp drive, while requiring exotic matter that may not exist, would allow a spacecraft to travel faster than light by contracting space in front and expanding space behind. Such a vessel could potentially carry observation equipment to distant locations, and return with information faster than light could make the round trip through normal space. Even if full-scale warp drives prove impossible, smaller-scale space-time manipulation might enable the creation of gravitational lenses or space-time telescopes that could bend light paths to observe regions of the universe that would otherwise be hidden. By carefully controlling the curvature of space-time, we might be able to create optical effects that allow us to see around cosmic horizons or observe events from multiple perspectives simultaneously. The possibility of extra dimensions, predicted by string theory and other advanced theoretical frameworks, offers another potential route to faster-than-light observation. If our three-dimensional space is embedded in a higher dimensional reality, it might be possible to observe events by accessing these extra dimensions, potentially allowing information to travel through shortcuts that bypass the light speed limit in our familiar three-dimensional space. Such extra-dimensional observation might require technologies that can manipulate or access dimensions beyond our normal experience. While this sounds like pure science fiction, some theoretical models suggest that gravity might already operate partially through extra dimensions, which could explain why it is so much weaker than the other fundamental forces. If we could learn to control gravitational effects, we might gain access to extra-dimensional physics. Advanced artificial intelligence and quantum computing might also play roles in observing faster-than-light phenomena. Quantum computers that can process vast amounts of quantum-entangled information simultaneously might be able to detect patterns or correlations that reveal faster-than-light effects, even if these effects cannot be directly observed through conventional means. Machine learning algorithms trained on enormous datasets of astronomical observations might identify subtle correlations that suggest faster-than-light communication between distant cosmic objects. While such correlations might have conventional explanations, the pattern recognition capabilities of advanced AI could help us identify candidate phenomena for further investigation. The search for extraterrestrial intelligence might also provide clues about faster-than-light observation technologies. Advanced civilizations, if they exist, might have developed technologies for faster-than-light communication or observation that we have not yet imagined. The detection of signals or artifacts that appear to violate light speed limitations could provide evidence for such technologies. Even if we never discover direct faster-than-light phenomena, the search itself drives advances in our understanding of fundamental physics. The technologies developed to probe the boundaries of light speed limitations often reveal new phenomena and capabilities that expand our observational reach in unexpected ways. Particle accelerators that push matter to ever higher speeds approaching light speed provide laboratories for testing the boundaries of relativistic physics. While no confirmed faster-than-light particles have been discovered, these experiments continue to probe exotic quantum effects and field phenomena that might reveal new physics beyond our current understanding. Future space-based observatories operating far from Earth's gravitational field and atmospheric interference might achieve unprecedented sensitivity to exotic phenomena. Large arrays of detectors spread across the solar system could create baseline telescopes with resolution capabilities that might reveal faster-than-light effects, too subtle to detect with current instruments. The development of room temperature superconductors, metamaterials with negative refractive indices, and other exotic materials might enable new forms of electromagnetic manipulation that could create apparent faster-than-light effects or enhance our ability to observe such phenomena. These materials could potentially bend electromagnetic fields in ways that create shortcuts for information, transmission, or reveal hidden aspects of electromagnetic propagation. As you contemplate these speculative possibilities, imagine humanity's future expansion into a cosmic civilization that has learned to transcend the apparent limitations of light speed through deep understanding of space, time, and the fundamental structure of reality. Perhaps advanced beings navigate the cosmos not by traveling through space, but by manipulating space itself to bring distant locations within reach. Such a civilization might observe the universe through networks of quantum-entangled sensors, space-time telescopes that bend light around cosmic horizons, or extra-dimensional viewing technologies that reveal hidden aspects of cosmic structure and evolution. The speed of light barrier that seems so absolute to us might be merely the first of many cosmic boundaries that intelligent life learns to transcend. Yet, even if faster-than-light observation proves forever impossible, The quest to understand and potentially transcend light speed limitations continues to drive human curiosity and scientific advancement. Each attempt to probe beyond this cosmic boundary teaches us more about the fundamental nature of reality and pushes the boundaries of what we thought possible. The question of whether we can see beyond the speed of light ultimately becomes a question about the limits of knowledge itself. Perhaps the true barrier is not the speed of light, but the boundaries of our current imagination and understanding. As we continue to explore the deepest mysteries of existence, we might discover that the universe holds secrets that transcend all the limitations we currently perceive as absolute. As we reach the deepest layers of our exploration into the nature of light's speed, we encounter questions that transcend physics and enter the realm of philosophy. The speed of light is not merely a measurement or a cosmic speed limit, it is a window into the fundamental nature of existence itself. Through this cosmic constant, we glimpse the profound interconnectedness of space, time, causality, and consciousness, revealing that the boundaries between observer and observed, between mind and universe, may be far more fluid than our everyday experience suggests. The philosophical implications of light's speed begin with the recognition that all knowledge of the external world comes to us through electromagnetic radiation. Every sight, every measurement, every observation depends on photons carrying information from the observed object to our eyes or instruments. In a very real sense, we do not observe the universe directly, but only the light that the universe sends to us. We are forever separated from direct contact with external reality by the finite speed of light. This separation creates what philosophers call the problem of the external world. How can we be certain that the universe we observe through light actually exists as we perceive it? The delay inherent in light's finite speed means we never see anything as it is now, only as it was when the light began its journey toward us. We live in a universe of echoes, reverberations of past events that may no longer represent current reality. Yet this same delay that seems to separate us from the external world also reveals a profound unity. The light entering your eyes at this moment has traveled from its source to you, creating a physical connection across space and time. The photons that allow you to see are the same photons that left distant stars, carrying within them the actual substance of those stellar furnaces. In a literal sense, we are touched by starlight, connected to the cosmos through the very medium that seems to separate us from it. This connection through light suggests that the boundaries between self and universe are less absolute than they appear. When you look at a star, photons from that star enter your eye and trigger neural responses in your brain. For a brief moment, the star's light becomes part of your consciousness. The distinction between the observer and the observed becomes blurred at the fundamental level where light mediates all observation. The speed of light also plays a crucial role in shaping our understanding of free will and determinism. If the universe operates according to deterministic laws, with each moment fully determined by the previous moment, then the future would be as fixed as the past. However, the light cone structure created by the finite speed of light introduces a fundamental limitation on determinism. Events cannot be influenced by other events outside their light cones, creating regions of causal independence that might preserve genuine freedom. This causal structure suggests that the future is not rigidly determined by the past, but emerges through a complex interplay of causal influences that can only propagate at the speed of light. Your choices in the present moment cannot be determined by events in your future, because causal influences cannot travel backward in time faster than light. The speed of light creates a protective barrier around the present moment, shielding it from deterministic influence by future events. The relationship between consciousness and the speed of light raises even deeper philosophical questions. If consciousness plays a role in the collapse of quantum states, as some interpretations of quantum mechanics suggest, then the speed of light might determine how quickly conscious observation can influence physical reality. Consciousness might propagate its effects through the universe at the speed of light, creating a moving boundary between quantum possibility and classical actuality. This possibility transforms consciousness from a passive observer of reality into an active participant in its creation. The speed of light would then represent not just the speed of information, but the speed of consciousness itself, as it participates in the ongoing creation of reality through quantum measurement and observation. The philosophical concept of time takes on new meaning when viewed through the lens of light speed. Our everyday experience of time as a flowing river from past to future may be an illusion created by our existence as massive beings bound to travel slower than light. From the perspective of light itself, all moments exist simultaneously in an eternal present. This suggests that our perception of temporal flow might be a limitation of our particular mode of existence, rather than a fundamental feature of reality. If time is indeed more like the block universe suggested by relativity, with all moments existing simultaneously, then the speed of light becomes the rate at which we traverse this four-dimensional landscape of space-time. Our journey from past to future through the block universe occurs at the speed of light, with consciousness serving as the moving spotlight that illuminates different moments in the eternal structure of space-time. The concept of identity and selfhood also faces challenges from the physics of light speed. The light that allows you to see your reflection in a mirror takes time to travel from your face to the mirror and back to your eyes. You are never seeing yourself as you are now, but as you were a tiny fraction of a second ago. This delay, while minuscule, reveals that even self-perception is mediated by the finite speed of light. On cosmic scales, this temporal displacement becomes more significant. If you could observe yourself from a great distance, you would see yourself as you existed years ago, when the light began its journey. From the perspective of distant observers, you exist not just as your current self, but as an extended trail through space-time, a world line of all the moments you have existed, all simultaneously visible depending on the observer's distance and relative motion. This extended existence through space-time challenges our notion of identity as localized in space and time. You are not just a momentary configuration of matter and energy, but a four-dimensional structure extending through the block universe, with different aspects of your existence visible to observers at different locations and moving at different speeds. The speed of light also illuminates the relationship between knowledge and reality. Since all information about the external world reaches us at the speed of light, there is an inherent uncertainty in our knowledge of distant events. We can never know what is happening now in distant locations, only what was happening when the light we observe began its journey. This creates fundamental epistemological limitations that cannot be overcome by better technology or more precise measurements. Yet this limitation also reveals the democratic nature of cosmic observation. Every conscious being in the universe faces the same fundamental constraints imposed by the speed of light. An advanced alien civilization billions of light years away would face the same delays and uncertainties in observing our galaxy that we face in observing theirs. The speed of light creates a level playing field for cosmic observation, ensuring that no observer can gain privileged access to immediate knowledge of distant events. The anthropic principle, which suggests that the universe appears fine-tuned for the existence of conscious observers, takes on new significance when considered in relation to the speed of light. If light traveled much faster, the universe might be so strongly connected by instantaneous causal influences that complex structures could not form. If light traveled much slower, cosmic evolution might be so isolated that information could not propagate effectively across cosmic scales. The actual speed of light might represent a sweet spot that allows for both cosmic unity and local independence, enabling the formation of complex structures while maintaining the information flows necessary for cosmic evolution. This suggests that consciousness and the speed of light might be intimately connected aspects of a universe that is fundamentally suited for the emergence of awareness and understanding. The philosophical implications of quantum entanglement, with its instantaneous correlations across arbitrary distances, challenge our understanding of locality and separateness. While entanglement cannot be used for faster-than-light communication, it demonstrates that quantum systems can share a unified state that transcends spatial separation. This quantum non-locality suggests that the separateness we observe in the classical world might be an illusion created by our macroscopic perspective. If reality is fundamentally non-local at the quantum level, then the speed of light barrier that seems to enforce separation in the classical world might be an emergent property that arises from quantum decoherence and the transition from quantum to classical behavior. The deepest level of reality might be completely unified, with the appearance of separation and the importance of light speed limitations emerging only at larger scales. The search for a theory of quantum gravity which would unify general relativity with quantum mechanics, might reveal that space and time themselves are emergent properties arising from more fundamental quantum information processing. In such theories, the speed of light would represent the rate at which information can be processed at the most fundamental level of reality, rather than a speed limit for motion through pre-existing space and time. This information-theoretic view of physics suggests that the universe might be fundamentally computational, with the speed of light representing the clock speed of the cosmic computer that generates the appearance of space, time, and matter through quantum information processing. Reality would then be more like a vast simulation running on quantum hardware, with the speed of light determining the frame rate of this cosmic computation. The implications for human meaning and purpose in such a universe are profound. If consciousness is fundamental to the collapse of quantum states and the emergence of classical reality, then conscious observers might be essential participants in the ongoing creation of the universe. The speed of light would represent the rate at which consciousness can participate in this cosmic creation process, making every conscious being a collaborator in the fundamental processes that generate reality. As you drift into the deepest contemplation of these mysteries, imagine yourself not as a separate observer of an external universe, but as an integral part of a vast, interconnected system of consciousness, information, and reality creation. The speed of light becomes the heartbeat of this cosmic system, the rate at which information flows, consciousness participates, and reality unfolds from quantum possibility into classical actuality. In this view, the question of whether the speed of light is an illusion transforms into a recognition that all boundaries, all limitations, all separations might be temporary features of our current level of understanding. The speed of light barrier might not be a wall to be broken through, but a teacher to be understood, guiding us toward deeper insights about the nature of existence itself. Perhaps the ultimate philosophical implication of light's speed is that it points us toward a universe far more unified, interconnected, and participatory than our everyday experience suggests. The barriers that seem to separate us from distant stars and distant times might be invitations to recognize our profound connection to the cosmic whole, mediated by the light that carries the universe to us and carries us into ever deeper understanding of our place within the magnificent tapestry of existence. As our journey through the mysteries of light's speed draws to a close, we find ourselves not at an ending, but at a beginning. The speed of light, which seemed so straightforward when we first encountered it as a simple measurement, has revealed itself to be a gateway into the deepest mysteries of existence. Through this cosmic constant, we have glimpsed the fluid nature of time, the interconnectedness of all things, and the possibility that reality itself might be far stranger and more wonderful than we ever imagined. The question we began with, whether the speed of light is an illusion, has transformed during our exploration. We have discovered that the answer depends not just on physics, but on how we understand the nature of reality itself. If the speed of light is an illusion, it is an illusion that reveals deeper truths about the structure of space-time, the role of consciousness, and the fundamental unity underlying the apparent diversity of the cosmos. Perhaps the true illusion is not the speed of light itself, but our perception of it as a barrier or limitation. What appears to be a cosmic speed limit might actually be an invitation to deeper understanding, a clue pointing toward aspects of reality that transcend our everyday experience of space and time. The boundaries that seem so absolute from our current perspective might dissolve as we develop new ways of understanding the nature of existence. Throughout our exploration, we have seen how the speed of light connects seemingly disparate phenomena across the vast scales of the universe. From the quantum realm where particles exist in superposition until observed, to the cosmic realm where galaxies race away from us through expanding space, light serves as both messenger and mediator, carrying information while simultaneously shaping the very structure of space-time through which it travels. We have witnessed light's strange relationship with time, existing in an eternal present while enabling us to peer into the cosmic past. We have explored how quantum mechanics reveals the participatory nature of reality, where observation and consciousness might play fundamental roles in determining which possibilities become actual events. We have considered the possibility that physical constants might evolve over cosmic time, suggesting that even our most fundamental understanding of reality might be temporary features of our current cosmic epoch. The speed of light has shown us that causality itself has structure and limitations, creating light cones that determine which events can influence each other while protecting the logical consistency of the universe. Yet we have also seen hints that this structure might not be as rigid as it appears, with quantum entanglement creating instantaneous correlations that transcend spatial separation, and cosmic inflation demonstrating that space itself can expand faster than light. We have contemplated exotic possibilities like warp drives and traversable wormholes, theoretical constructs that might allow effective, faster-than-light travel without violating the principles of relativity. While these remain highly speculative, they illustrate how apparent limitations in physics often point toward deeper principles that we have not yet fully understood. The philosophical implications of our journey extend far beyond physics into questions about the nature of consciousness, identity, and reality itself. We have seen how the finite speed of light mediates all our knowledge of the external world, creating both separation and connection between observer and observed. We have explored how this might shape our understanding of free will, determinism, and the role of consciousness in the unfolding of reality. Perhaps most profoundly, we have discovered that the speed of light might be telling us something fundamental about the participatory nature of existence. If consciousness plays a role in quantum measurement and the collapse of possibilities into actualities, then the speed of light might represent the rate at which consciousness can participate in the ongoing creation of reality. This participatory view transforms us from passive observers of a predetermined universe into active participants in the cosmic process of becoming. The speed of light becomes not a barrier that separates us from the rest of the universe, but the medium through which we remain connected to the cosmic whole, receiving information from distant reaches of space and time, while contributing our own observations and choices to the ongoing evolution of reality. As you rest in these final moments of contemplation, imagine the speed of light, not as a wall that confines us, but as a bridge that connects us to everything that has ever been or might ever be. Every photon that enters your awareness carries within it a piece of the cosmic story, connecting you to the nuclear fires of distant stars, the ancient glow of the early universe, and the ongoing dance of matter and energy across cosmic scales. The light that illuminates your world tonight began its journey in the distant past, perhaps in the heart of a star that died billions of years ago, or in the quantum vacuum fluctuations that preceded the first moments after the Big Bang. This light has traveled across unimaginable distances and vast stretches of time to reach you in this moment, carrying within it the history of the cosmos and the potential for future discovery. In receiving this light, you become part of the cosmic story yourself. Your observations, your consciousness, your very existence as an aware being capable of contemplating these mysteries contributes to the ongoing process through which the universe comes to know itself. The speed of light ensures that your perspective, like every other conscious viewpoint in the cosmos, adds something unique and irreplaceable to the total understanding of existence. The question of whether we will ever transcend the speed of light barrier may miss the deeper point revealed by our exploration. Perhaps the goal is not to break through limitations, but to recognize the profound interconnectedness and participatory nature of reality that these apparent limitations reveal. The speed of light might not be a prison to escape, but a teacher to understand, guiding us toward ever deeper appreciation of our place in the cosmic whole. Future generations may develop technologies and insights that make our current understanding of light speed limitations seem as quaint as ancient beliefs that the Earth was the center of the universe. They might discover shortcuts through extra dimensions, learn to manipulate space-time itself, or develop forms of consciousness that transcend the ordinary boundaries of space and time. Or perhaps they will discover that the real revolution comes not from transcending physical limitations, but from recognizing that consciousness itself is fundamental to the structure of reality. In such a universe, the speed of light might represent not a barrier to be overcome, but the natural rhythm of cosmic awakening, the rate at which awareness flowers throughout the universe and comes to recognize its own infinite nature. The speed of light may indeed be an illusion, but if so, it is an illusion that points us toward truths more profound than any literal interpretation could provide. In contemplating light's speed, we contemplate the nature of time, space, causality, and consciousness itself. We encounter the mystery of how finite beings embedded in local space and time can nonetheless participate in cosmic understanding that transcends all apparent boundaries. As you drift into peaceful sleep, let the mystery of light's speed carry you into dreams of cosmic connection and infinite possibility. Rest in the knowledge that you are not separate from the universe you observe, but intimately connected to it through the light that reaches you from distant stars and carries your own influence outward into the cosmic community of conscious beings. The speed of light, whether illusion or absolute reality, has given us a gift beyond measure. It has shown us that we live in a universe where mystery and understanding, limitation and transcendence, separation and unity, all coexist in the delicate dance of existence. In this cosmic dance, every conscious being has a part to play, every observation contributes to the whole, and every moment of awareness adds another note to the infinite symphony of cosmic awakening. Sleep well, cosmic voyager, knowing that tomorrow will bring new opportunities to explore the endless mystery of existence, guided by the light that connects all things and the consciousness that allows the universe to know and celebrate its own magnificent complexity.